Welcome, class, to this Masterclass Explainer on the Open Knowledge Format, or OKF. Look, if you're going to engineer modern autonomous AI systems, you absolutely have to understand context engineering. Today, we're going to deconstruct exactly how to solve the critical context assembly bottleneck that's been holding back agentic AI. I want you to treat this as a core module in your advanced computer science curriculum. Let's get right into it. Okay, let's quickly hit our syllabus for today. We'll be covering the context assembly problem, architectural axioms, structural versus semantic interoperability, the progressive disclosure pattern, technical syntax, and finally, managing semantic drift. Section 1. The context assembly problem. We're kicking off our curriculum with a bit of an autopsy on corporate data architecture. As future systems architects, you're going to confront the classic N+1 surface problem. It's literally a tale as old as time in software engineering. When you try to build a centralized registry to unify n number of fragmented systems, legacy wikis, code comments, metadata catalogs, you usually don't end up deprecating the old ones. You just create the N+1 silo, complete with its very own proprietary APIs, access controls, and custom SDKs. You basically trap the knowledge behind yet another software barrier. So, the big question is, how do we escape this? This elegantly illustrates the paradigm shift proposed by Google Cloud engineers. Instead of a centralized proprietary microservice dealing with high API latency and clunky custom SDKs, the open knowledge format completely abandons proprietary runtime dependencies. It favors a distributed file system native directory tree of flat files using raw markdown parsing. Language models can ingest this directly with almost zero latency. It's a format, guys, not a service. That is a game changer. Section 2. Architectural axioms. Let's explore the actual structural blueprint of an OKF bundle and see how it elegantly resolves programmatic identity. Now, in traditional databases, you need these abstract hash values or view IDs just to verify an identity. But in this architecture, your concept ID is derived directly from the physical directory layout itself. It's simply the deterministic bundle relative file path, just with the .md extension removed. By doing this, your identifiers remain completely human-readable, they're logically isolated within their folder namespaces, and they are naturally structured for an AI agent to parse. Right alongside your custom concept documents, the OKF specification reserves a few specific file names to guarantee structural predictability across the whole file system topology. You'll always see an index.md, which is strictly reserved for directory listings and progressive disclosure, and a log.md, which is reserved for chronological append-only update histories. Every other custom markdown file in there just acts as a single conceptual atom. Section 3, structural versus semantic interoperability. This brings us to an absolutely crucial design philosophy. A brilliantly engineered system knows exactly what to standardize and exactly what to leave open. OKF strictly standardizes the structural shape of the container. It actually requires only one metadata key across the entire format, and that's the type field. But it leaves semantic interoperability completely open. Why? Well, to avoid standard-setting gridlock. A data engineering team might call an asset a BigQuery table, while DevOps just calls it a table. Agents can just analyze the surrounding natural language to bridge that gap. This allows for immediate adoption across massive enterprise teams without getting bogged down in endless committee meetings. Section 4. The progressive disclosure pattern. So how do we actually solve context window pollution and token exhaustion when we're doing semantic search? We use what's called the progressive disclosure pattern. Dumping a massive corporate wiki directly into a prompt is a disaster. It exhausts token capacity and causes wild model hallucinations. Progressive disclosure instead acts as a nested registry. It utilizes top-level index.md files to guide agents down localized, highly relevant traversal paths. This is literally the cure for model hallucinations. Instead of dumping raw, noisy data into an LLM, we're feeding it a structured map. The agent just executes this simple, step-by-step traversal algorithm. Step 1, read the root index.md. Step 2, identify the relevant subfolder path for its specific task. Step 3, retrieve the specific concept documents. Boom! It isolates the exact context required for its localized task, completely bypassing the need to ingest the rest of the repository's noise. For the computer scientists in the room, let's actually look at the math here. The absolute value of P, which is the active traversal path, plus the absolute value of K, the retrieved concepts, is much, much less than n, the total number of concepts in the repository. Mathematically, this means your token consumption scales logarithmically compared to the linear scaling of traditional full repository ingestion. You are maximizing your computational token efficiency big time. Section 5. Technical syntax and implementation. Okay, let's deconstruct the required anatomical layers of a single OKF concept document. Every OKF document has a strict contract. It kicks off with a triple hyphen YAML front matter block, and that block must contain that single required type field we talked about earlier. Right below that is the markdown body containing your natural language prose for relationship extraction. Finally, relational links are mapped horizontally using absolute bundle relative paths that always start with a /. Now, just to avoid namespace collisions in practice, practical tools like Stashpad will actually prefix custom keys in the workspace and then dynamically map them back to standard OKF front matter during their production exports. I really want you to burn this quote into your minds. Zero SDK dependency, readable via standard terminal utilities. This rule is absolute paramount. It's exactly why reference utilities, like the Cytoscape-powered HTML visualizer published by the standard's creators, can render entire, highly complex context graphs completely locally in a browser, without any back-end runtime whatsoever. No company data ever has to leave the local network. That is huge for enterprise security. When we step back and evaluate what we call the modern agent-readable stack, you can really see how OKF fits into the bigger picture. You've got sitemap.xml doing the basic crawler routing, you've got llms.txt giving those high-level summaries, and agentsmd mapping out code-based behavior. OKF sits right at the top layer. It provides the dense, structural content library, a nested directory tree that perfectly complements those higher-level protocols and actually allows agents to perform highly complex reasoning tasks. Section 6. Managing semantic drift. For your final assignment in this explainer, we have to look at system maintenance. Semantic drift, that inevitable divergence between your real-world system state and your written documentation, is absolutely going to happen. To prevent it, your engineering response needs to follow these 3 steps. First, integrate your OKF bundles directly into your code repositories. Commit the markdown files right alongside the source code they describe. This brilliantly aligns your documentation lifecycles with standard software deployment rules, taking full advantage of pull requests and branch protections. Then you implement CI/CD validation gates, and finally, you establish human-in-the-loop curation policies. Let's drill down into that CI/CD step for a second. You absolutely must implement strict automated validation gates on every single pull request. Your automated pipeline checks have to verify non-empty type properties in the front matter. They must test and resolve all bundle-relative internal paths so there are 0 broken links confusing your agents. And they must enforce that those index.md and log.md structural constraints remain perfectly intact. Doing this ensures your downstream agents only ever operate with an accurate, totally verified system constraints. So the crucial point we are leaving you with today is this. Context is no longer some centralized service you have to buy from a vendor. It is a local file structure to be cleanly engineered by you. As future systems architects equipped with the open knowledge format, what will you build with it? Class dismissed, and we'll see you in the next explainer.